I am here to introduce tonight's talk and talk to you a little bit about the organization that is facilitating it. Windsor Hackforge is a community organization that is dedicated to learning and sharing in the tech community in Windsor. And if that sounds good to you, we would love to hear from you, and we would love to meet you and maybe see you present at a future event. And if you're interested in that, you should check out our website at hackf.org. We would love to see you visit and hear from you. And with that, I will now turn the microphone over to Fraser Fathers until it's time for me to contribute again. Fraser?
Thanks so much, Doug. Good evening, everyone. I'm just going to share my screen real quick here. So tonight I'm joined by my colleague Chris and Gordon as well. He should be joining. He's running a moment late. And we're going to talk to you about a project that we've been working on for the better part. I've been working at least on this project for a better part of 2 years. But the main project that just went live last week is called ADUSearch. So you can find it at ADUSearch.ca. We're not going to do a live demo here. What Doug sort of asked for us was, could we dig into some of the tech and the tools that were a part of building this tool that really is designed to help people understand the potential of their own backyard. And so really quickly, what we're going to talk about before we hand it off to Doug tonight is really what is ADUSearch? What was our process to get to geospatial analysis? I'm going to turn it over to Chris and Gordon at the geospatial analysis. They're two GIS researchers, amazing guys. Have done some awesome work on this project. They're going to talk through some of the technical details of what they did, both in like tools like Arc, but also in Python and other tools like that. And then from there, once we get to sort of where we get to our final product, where we handed it off to Parallel 42 and Doug as part of our project, that's where we'll hand it off to him. And he'll join back in to talk about some of the technical web-based work that him and his team did as a part of this project. At any point in time, I believe, you can drop messages in the chat and we'll try and get any questions that you guys have answered as we go. Otherwise, you can save stuff to the end. I don't expect us to sort of be running super long here. So yeah. So just really quickly, so ADUSearch wouldn't have been possible without a whole bunch of partners and funders. So the project was funded by the Canada Mortgage and Housing Corporation as a part of the Housing Supply Challenge Round 1, which was the Data Creation Challenge. And really our goal was to create new data on the housing system in order to better understand the system. Our project has been housed for the last 2 years with Family Service Windsor Essex. Family Services Family Service pretty much is our a local nonprofit organization, which housed our project for the last couple of years. And you can see all the partners that we had both locally and more further afield, like the School of Cities, Terranet, Alt Atlas, the Essex Region Conservation Authority, the Cross Border Institute, MPAC, and Parallel 42. We also had municipal partnerships across the country to help achieve the goal of this, our goals of this project. So really the goal of ADUSearch is to discover the potential of your own backyard. And for those that don't know, an additional dwelling unit, ADU, also called laneway suite, garden suite, backyard cottage. There's about 50 technical terms for what these things are. ARUs, additional residential units, is the technical term that the province of Ontario wants you to use, which we don't use. They're in essence additional housing options that can be built on existing residential property. And so what we were striving to do is really better understand what is possible based on existing residential properties, how many additional units based on current zoning and bylaws would be allowed in a given city. Spoiler alert, we worked through about 2.5 million lots. We mapped over 2.5 million lots across the country, and about 900,000 of them could, as of right now, build an additional dwelling unit in their backyard. The exact size and shape depends a little bit, depending on the municipality, but more or less about 900,000 residential lots could have an additional unit added today if the resources and if the people who own those lots really wanted to. So really the goal, and our project's growing and evolving currently, into a future sort of state. Now that we've launched sort of the first iteration of the tool, or the first full national iteration of the tool. And so it's really about providing resources to people to better understand what the opportunity and what the potential is in their own backyard. So this is just a brief timeline of where we started. Started here in Windsor back in July of 2020. A conversation with myself and our co-lead, the co-lead, she couldn't be here this evening, but Sarah Sipkar. She actually built an ADU in her backyard, so she has firsthand sort of development experience on building one. And we ended up proposing to apply to the Housing Supply Challenge in 2021. That enabled us to create, and maybe you saw, our original proof of concept tool, which was just for the city of Windsor. And we were successful in using that proof of concept, and after we were funded through CMHC to create that proof of concept, to actually scale up nationally. And we had an ambitious goal of trying to get almost 100 cities in the tool. We ended up getting about 30, and there's a variety of reasons about that, and we can talk about that if you want. But really, we've now launched the new version of the tool. We had a national team of over 12, team members across the country, all working remote. And we've been working cross-functionally with industry partners and national stakeholders to really get this tool live and really understand what's possible across the country from an ADU perspective. And as we move into our future state, April 23 beyond, there's going to be a lot more research and other products being developed by ADUSearch as things sort of move forward. So our process really had 3 major stages, and different groups sort of on our team or in partnership with our team did each of those stages. So the first, there was a policy and financial research, and processes are all around that. And I'm going to talk about that in a bit more detail. Then we had a geospatial processing portion of the tool, which Chris and Gordon are going to talk about. And then finally, we had the web development piece, which is where we'll hand it back over to Doug to speak sort of from a tech perspective around what it took to actually get the tool online and make it functional from the user experience that you see today. So that's really what we're going to talk through today, is that journey. So where we started with this whole project is municipal bylaws. And these are not exciting documents. These are not fun documents. These are several hundred pages long documents, generally in a not user-friendly PDF on a municipal website buried somewhere after 3 or 4 sub-pages. And what we had to do was actually go through for each municipality and determine, are ADUs possible in that municipality and under what circumstances? And so that meant categorizing things like zoning types, building types, types of secondary buildings allowed on lots. What were the lot coverages and setbacks requirements? Are they in a floodplain? Are they, what are the parking requirements? All of those things had to be sort of categorized and mapped across the country. And this was an input that became incredibly important for the geospatial modeling, because if we didn't know exactly how far the setback needed to be in the backyard in Brampton, we would have no idea if it's actually physically possible to build an ADU there, if their bylaws even allow for an ADU. We found a number of municipalities where, despite being a large or mid-sized city, they don't allow ADUs right now. And so part of what ADUSearch is hoping to do is start conversations about allowing these to be built in certain communities, while also making it easier for a homeowner or a policymaker to explore what's possible in the community itself. So all of this got mapped in giant spreadsheets for each municipality. And what it turned into is a flow chart like this. And this is, I believe, for Brantford. I just sort of randomly pulled one out of our database that we have. And what this flow chart represents is, in essence, all of the gateways and the steps that an individual lot would need to go through in order to potentially get to a point where it's like green light. Yes, you can build an ADU. And so many of these, in each of those little black dots, you can't read what's on the screen here. That's not really important. What's on the screen here is a gateway that had to be processed geospatially. And we had to determine whether or not, that particular step, whether is this lot have a main dwelling on it, or is it just a vacant lot? Is this lot zoned correctly? Is this lot, have a single detached home or a row house or a semi-detached house? All of those things influence, whether or not a particular property moves through this whole flow chart. And then you get into a series of calculations around areas and stuff like that, which I'll leave a little bit for Chris to talk about in a bit. But what it leads to is, in essence, turning that flow chart into, in essence, a database for us. And what we had to do was work through each of these checks and determine whether or not a lot is or is not actually able to build an ADU. And so you can sort of see here, the first one there with all ones, well, that got to the end, and that's green. That lot would be good to go. The second row there, yeah, it fails the lot coverage. Well, what does that mean? It means that there's too many buildings already on the lot. The town won't allow you to actually build another structure there. So you have to either maybe tear down say you had a detached garage, I have to tear that down. Or maybe the house is just oversized for the lot and you just can't. But it might mean you can put an ADU in your basement or in your attic or something like that. Third, ones down here, straight zeros. Pretty much they're not zoned right. So they're residential, but they're not zoned properly, which means in essence that, maybe it's an apartment building. You're not putting a tiny house on the roof of, a 30-story condo building. So the idea around that is really just this lot isn't eligible for an ADU based on the zoning. So it shows up red. And in essence, where we end up is with a scoring system like this. And so you'll look currently on ADUSearch.ca, you'll see sort of every municipality has a breakdown sort of using this sort of scale around what is or isn't suitable on a lot by lot basis in their municipality. So red means in essence, generally it's, like a red light. Pretty much you're not zoned right or the buildings don't meet general requirement. And usually that is a major barrier. In other words, you're not going to rezone your single family home into something else to let you to build an ADU. Most people aren't going to go through that process. Yellow means that generally you're not meeting lot coverage, meaning you can't add additional buildings. Usually this happens when the lots are undersized or there's some other detached structure there. So like you have a detached garage that counts as building coverage on the lot, but it doesn't necessarily mean you can't put a basement apartment or an internal apartment within the existing structures. So you could maybe build something or add an additional unit on that lot, but it's not going to be a tiny house in your backyard. Light green, potentially suitable, means that you meet requirement, but usually there's some extra step that has to be met. Quite common ones that we saw were tree cutting permits, floodplain sensitivities, where you need to go get an extra permit from the Conservation Authority in the case of floodplaning. If you have an oversized tree in your lot, for example, you sometimes need to get special permits in Toronto, Winnipeg as an example. If you have a tree greater than 30 centimeters in sort of thickness, you have to get a permit to cut it down because they're trying to maintain their tree coverage. And then finally, dark green or suitable. More or less, you've met all the requirements to build an ADU. And generally speaking, it means that green means go. You should not have significant barriers based on the data that we have available to building one of these structures in your backyard. And what you'll see, and Chris will talk about, is lots that show up dark green actually have on the map an area highlighted to say this is your buildable area for ADUs in your community. One thing that we're not going to talk about a lot right now, but is in our data, is then aggregation. So everything we talked about up till now is on a lot by lot basis, 2.5 million lots. But what we did is we aggregated all this data to a census dissemination area, which we call a neighborhood generally. But in essence, it allows us to aggregate it to other common boundaries so that you can mesh this data together with things like census data in order to do some additional analysis. So you'll find a neighborhood view on our website. And within that neighborhood view, there's actually 4 DA level layers. There's an aggregation layer, which just sort of aggregates all the lot by lot data up. So it takes an average lot size, takes the number of green, yellows, and red lots in a particular neighborhood, etc. There are 2 affordability layers, one for homeowners and one for renters. We did a whole bunch of financial modeling around that. And then finally, there's a national minimum regulation layer, which in essence takes a sort of best in class, super lax set of bylaws and applies it to the municipality. And it tells us, in essence, what the difference is between what the current bylaw says and what if you were to take the most loose standards from across the country and apply it to that municipalities, how many lots would be actually up for or eligible for an ADU. By the end of March, data for all of this will be available on our open data portal for all the municipalities. We just couldn't get it ready for launch in time. So in the coming weeks, you should check back if you're interested in digging into some of this data at an aggregate level, as that will be freely available for people to access. So at this point, I'm going to turn it over to Chris and let him sort of start working his way through the actual geospatial analysis, and then we'll go from there.
Thanks, Fraser, and thank everyone for coming. Just to reiterate, my name is Chris McLeod, and I've been one of the GIS researchers on the project, which handled more of the technical side, all the spatial data and the processing that was then handed off and checked over to Doug for the final submission. And so initially, the data we required, once we've got, as Fraser mentioned, all of our bylaw information, all of our inputs, what we want our data to look like, we need to go over what data we need. And so the three core files that we needed for the bare minimum, where we just wanted to make shapes, essentially, given the data, would be the parcel file, the building footprint file, and the street or the road network file. And with these three, we can build up the general buildable ADU area on a lot by lot level. But without extra data files, a lot of context is missing from that information, stuff that we need to make the data make sense. And with that, we would need the zoning file, address points for cleaner addresses. So people, would be able to look up their lot. Everything would make sense from that point. And the floodplain and regulated areas polygon file, which would more often be supplemental. It wouldn't necessarily be required for many municipalities, as their bylaws differ between, municipality to municipality, city to city, in terms of whether a floodplain impacts whether you can build an ADU on your lot or not. But it's almost always important, as we found going back through, that it pops up more often than initially we had thought. So a lot of the time we get this data, we use open data portals from municipalities, which was given raw data. And raw data is often messy and uncategorized and sort of unwieldy. And in order to manipulate that data in the way we want to present our buildable ADU areas and our geospatial information, we need to clean that data. And so you can see in the example above, the raw data, there's often these missing or empty columns with no information to little information with them. And we need to combine all those files that was previously mentioned and clean that data to make it look presentable, but also usable. A lot of this is case sensitive information. So if our street name differs by a spelling error or has the wrong suffix compared to our parcel file with the same street name, we'll run into problems with that. We won't get that join that we're looking for and that harmony between all three files that we need. And so in the example below, you can kind of see we've got just general classifications of information we need. You've got street names, addresses, the parcel area, the house area. If there's a garage or a secondary structure, that would be found in garage area. The buildable ADU area is there, but we don't calculate that until later. This is just an example of sort of a finalized geodatabase from Winnipeg. But all these columns are essential and important, and we need to have that information readily available, readable to us, and clean to us so that we can use it in the future. So now we've got our data cleaned and organized and ready to go. We can take our three files there. You can see the building footprint file, the parcel file, and the street file, all lined up. All the street names match, which is the most important part for our processing. We need to find out how to differentiate the front yard from the rear yard. And the initial model that was done in order to do that was to buffer through 5-meter intervals, starting at 20 meters usually from the street, to see whether they intersect with that building footprint. So you can see in the examples there, that red section is the 20-meter buffer distance from the street. And most of the houses are within that buffer, but there are some that aren't. And so in the initial model, you would go 5 meters by 5 meters for every interval. And you'd select all those buildings within each interval and classify them justly. So every building within 20-meter buffer distance would be 20 meters. And Fraser, you could go over to the next slide there. And then there's a 25-meter buffer. Every building within the 25-meter buffer would be classified as 25-meter buffer. But because the 25-meter buffer also encapsulates the 20-meter buffer, you need to separate those into individual classes. So when we process the 25-meter buffer buildings, we're only processing just those 25-meter buffer buildings. We're going to process the 20-meter ones separately because we don't want to overlap our data. We're only going to run them by each category. So now that we've got our buffer distance sorted from the buildings and we can sort of define where that front yard intersects, we want to use a union tool. And essentially what the union tool does is combine as many spatial data sets as you'd like. However, you can only use polygon information for these, which is why we would use our buffer, our building, and our parcel file. And all these get combined into one file where intersections and crossover lines delineate the boundaries for those extra shapes. So given that we've now got our union file, which is all three of those files essentially up in one, we can delete the unnecessary polygons that we don't want to run statistics on. We don't want to run that geospatial analysis on, which would leave us with this. And you can see this is the 20-meter buffer section, but those front yard areas are cut out. So then we can build our, we can use this information to then buffer our buildable area in only the areas we're interested in, which is the rear yard. Typically, for almost nearly every municipality, it's rare that they would have front yard buildable area for ADUs. Very typically, you would have side or rear yard only, in which you would be able to construct an ADU in your yard. I believe the next slide. Yeah. So this is just the 20 meters. You can see the 25 meters haven't necessarily been run here. We would do the exact same process for the 25-meter areas. But you can see only the buildable area, those blue sections there, are showing up in exactly that rear yard spot. One of the drawbacks of this model was that we would end up with some ADU fragments in front yards or extra area in side yards where maybe we won't necessarily need them. So we can do a little bit of cleaning up there and remove those smaller fragments. But what happens if those fragments are the minimum size of an ADU in our yard, which you can see in the top there? There's two of those lots on the corner that have those fragments that meet the minimum size requirement. They would technically still be present in our data set, because if your municipality allowed you to build in the front yard or side yard, or you met that front yard setback, you would still be eligible to build ADUs there. And so this essentially was the product of our end model there. Sorry, Fraser, if you just go back one slide. Yeah, so this was essentially the end product of our model. Was we would have our spatial data and then our table data, which was all that clean data I showed off earlier, as well as our buildable areas. And this was the initial model run for Windsor, which met all the requirements and was fantastic. But then we ended up running into situations where municipalities specifically mentioned rear yard only ADUs. So those front yard fragments and that extra side yard buildable area was technically incorrect for these municipalities. You wouldn't be able to build an ADU there. So we elected to find a way to exclude and create definitions for front yard and rear yard. So one of the methods we came up with, which specifically, well, first of all, we need to define front yard and rear yard. And oftentimes in GIS, the spatial data has sort of no bearing until we give it one. So you can see just by looking, you can kind of tell where the front and rear yard is, but the programs don't know that. According to the programs, they're just shapes that have been placed in these specific spots. And so one of the methods we came up with to create, a clear division between front and rear yard is split the lot right down the middle of the building. And the first step to do that was to find the centroid of the building, which is the, center, the sort of the geodetic center of the building, not necessarily the exact center. And this was a pretty straightforward process, just converting those building polygons to building centroids. And then the next step was to calculate the closest point from those buildings to the road, because we want to orient the front yard to the direction of the road. We don't want to orient it, into the side yard or anything like that, because then we would end up with some very odd splitting lots. So we use that same method as joining the street name of the building and parcel to the street name in the street polygon or the street line file. And we would calculate the closest point from the building centroid to the street. And you can see those green dots are those points on the street, and the purple dots are the building centroids. And we can create a route between these 2 points. And a route's very important because apart from a line file, a route file allows us to calculate distance from a starting point to an end point, or varying distance along that route, or you can calculate speed and time and all sorts of things along the route. And we are mostly interested in the angle. So using the angle from the building to the street, we can create perpendicular lines from the building centroid, well, after we've normalized the angle along that route. And we can split the lot, or create these split lines rather, before we split the lot, given a perpendicular angle to our route connection to the street. And you can see this works on corner lots. It works on lots around curves. There can be some spatial troubles, but there's always spatial troubles with most data sets. That doesn't always line up completely. But we can, produce a clear definition between front yard and rear yard, given the strategy. And we can do the same method that we did previously, where we split, we use that union tool, and we ran only that buildable area check and those negative buffers on the lots that we were interested in, the very specific data that we cared about. And in this case would be our rear yard definitions. So given that we've defined our rear yard, this method, we don't need to split them into buffer distances because it's already been calculated with routes. We eliminate the front fragments of ADU buildable area that might be present in the front of the buildings or in the front yard. And we've also eliminated those side yard buildable areas, which we don't want to show. So we've been able to create a more accurate buildable area for these municipalities that require rear yard only. And we've ran into a number of these municipalities, but that's generally the stipulation that we need to sort of account for when it comes to working with these municipalities. We want to present our data as accurately as possible, and being able to eliminate all those extra fragments and redundancies helps quite a bit. So I believe I was supposed to pass it over to Gordon, as he was sort of the brain behind this next section. However, I'm not sure if he's here.
Yeah, I don't see him.
So I could just run over these.
Yep.
Another sort of stipulation or categorization for the municipalities that we ran into was municipalities that had very different front setbacks, side setbacks, and rear setbacks. So previously, when we were running those negative buffers, we were using it on the whole yard, because generally the side buffers and the rear buffers were the same. Very often they'd be the same. There's some municipalities that have very specific differences, like I think Barrie was a big one, where the rear yard buffer is either larger than the side yard, or it includes a front yard buffer, where you could still have technically ADU buildable area in the front of your yard if your building was far enough away and you still had enough area there. So Gordon and the team helped devise this extra strategy to go through, where we would select the parcels using the same buffer system that we did with the original model, but we would turn those parcels into line files first, and then we would use more proximity analysis to define these yard boundaries. So the first selection that was done was to calculate the front yards, because we want to buffer those individually. These were selected by totally within the buffer area. So if we were to select all our different lot lines individually by what are completely within that buffer section, only our front yards would be included. And this would go street by street, just like the other example. So those corner lots wouldn't get miscategorized by being within the buffer to a street that they don't belong to. It would only buffer and only connect to that street that they belong to. So you can see those green bars there. Those are our front yards. They're completely within just a 25-meter street buffer. Oftentimes, this measurement will change depending on the municipality, whether the parcels are further away from the street or closer. There's kind of take a little bit of adjustment there, depending on the municipality. But generally, the 25-meter measurement was good. That was like our general use case or sort of baseline statistic to go off of. And so our side yards, these were connected by just intersecting with that buffer. So they may not be completely within the buffer, but they're touching it. And these would all be our side yards. And these are only for interior lots, these highlighted ones here, as oftentimes external side buffers would have different measurements from interior lots. And so these ones were just categorized as sort of a general, at a general level. And then the more specific level would be the lines that do not touch other parcels. So the ones that are not intersecting with each other. Those are identified as external side boundaries. And those are classified correctly as those. You can see them highlighted there in pink. And then the rest was easy. The rest were just rear yards. So we've already classified our front yards. We've classified our side yards. All the things we haven't classified, they would be classified as rear yards. And you could do an accuracy check by checking if they've intersected the buffer at all. Sometimes you may get one stray lot that's very wonky shaped. You know, a lot of lots are not necessarily perfect rectangles like we'd love to work with. A lot of the times they could be just very odd shapes. And those would be outliers, but you can use a sort of selection process to kind of weed those out, or at least find those error spots that might pop up. You know, as much as we love working with clean data and this neighborhood example we've shown, it's not always the case. A lot of the time they can get a little wonky where maybe the buildings don't line up, the streets don't line up, the buffer doesn't line up, and you kind of have to make adjustments to that. And thankfully, a lot of the methods we came up with have a little bit room to kind of make those adjustments. And so here's an example here of a municipality that might allow for front yard buildable area or front yard ADUs with all the setbacks calculated on a lot by lot basis and a yard by yard basis, you know, all the boundaries. And the reason why we may not necessarily do this for every municipality is because this one takes a lot of time. The more spatial processes we're running on a municipality, the longer it takes. And so the first model is very fast. It uses very basic principles. The split line model can be slow, but in general, after our revisions, has been quite quick. And this one takes a lot more processes. So a lot of the time it's determining what model do we need to take on a municipality. You know, what are their bylaws and restrictions? What are their stipulations on where you can build an ADU? And how do we present, or how do we calculate rather, that presentable data given our processing time and accuracy? Those are the main fallbacks that we want to go back to. So now that we've got our buildable area set up, we want to organize our geodatabase for send off. And so this is an example of what a final geodatabase would look like once we've got all of our files done. After we finish the ADU buildable area, we do the aggregation, and that's where the DA layer would be. But we start with our classification here. So we've got our city name, just to start off with. This is the naming scheme that Doug and the team had given us to follow for best upload procedure. We start with our city name and then our SGC code, which allows for more specific classification on our cities rather than just relying on the name. And then we have our date and our timestamp. And this is really important for obviously archiving our data and repairing these errors, making sure that we have the most current data set up. We're not going back on an old data set. And so our spatial data that we're including in this geodatabase sort of acts like a container of all of our information, similar to a zip file, but specifically for geospatial information and table information. Those top three layers there, we've got our buildable ADU area, which is labeled ADU. We've got our building footprint layer labeled buildings, and we've got our dissemination area layer, our DA layer. Fraser showed off sort of an example of what that would look like. All of our aggregation and our statistics and our summaries that we ran on our data would be in that DA layer. We've got our parcel layer and we've got our streets layer. And those are the core spatial data layers that we would have in our data set. And those are the ones that you would see on our website. Essentially, all that visual representation without any of the numbers would be shown through those layers. And then we have our table data. We have our supplemental information that gives more context to our spatial data, linked through relationship classes and data tables. So our DA key was a table that linked our property IDs to the corresponding DA. Our data key was one that linked our data IDs, which would be in the data table, to our property IDs. We've got our parcel to DA and parcel to data relationship classes. And these were sort of that glue that joined the DA key between the DA and the parcels file and the data key with the data table and parcels file. And this allows us to, collect all this information and have it be consistent with each other. You'd be able to read all that data just simply through these relationship classes by making sure everything lines up. When you go look through the data, when it's presented, all of our data is accurate. One of the main reasons we split up sort of the data table information, which would be those gateways that Fraser showed off earlier, was that we need to keep our data consistent with each city. And so in our data, the ADU layer, the buildings layer, the DA layer, parcels layer, and the streets layer, all of our spatial data that you see on the website, all of that is consistent with every city uploaded. It all has the same fields, the same columns, the same data information that's there. And all the separate information that may vary between municipality and municipality, stuff that is going to be different between every city we work with, that would go in the data table. And then, so having that relationship class to separate those files, but still be viewable, is very important for keeping consistency in the upload. Now we've got our upload, we would send it off to Doug. We would upload it and it would be sort of out of our hands until maybe an error would come back.
Thanks, gentlemen. Fraser, do you have any final thoughts to add before we jump into the next section?
Nope.
Wonderful. Okay. So thank you guys. That was a really comprehensive and good overview of the research and geoprocessing piece of this. And the thing that I think is the through line, the thing that I want you to carry forward as we start now talking, and I'll just share my screen. Just as we start talking about the structure of the data pipeline and the application, I want you to keep in your mind the level of complexity that we're dealing with in that source data and all the possible ways that it could go wrong, all the possible ways that there could be a challenge or an issue. And that will help inform, I think, some of the choices that we made in our own design. So ADUSearch 1.0, at least that is sort of internally how we think about it. And before I go any further at all, I want to acknowledge a couple of people, actually. I see that of the 9 people at Parallel 42 who worked on ADUSearch at some point or another, we have Sharad Chand and Sherry Wheeler in the audience. Thank you so much. Sharad helped us quite a bit with ADUSearch 1.0, and Sherry was our primary web developer throughout both phases of the project. The other folks that I want to acknowledge, when we get to ADUSearch 2.0, you're going to see a significant upgrade in the visual style of the application, and that is down to the folks from Elevate who helped to bring forward a visual style and a design for this site that really helps it to sing, I think. So ADUSearch 1.0 was our prototype, our first kick at the can at this type of an application, and it was Windsor only. So compared to the ADUSearch project that we're looking at today on the website, it was pretty narrow in scope, just one municipality. We did not have a whole lot of fancy data validation or data processing. Our method of data transformation was primarily manual. We would take, at that time we were using Esri shapefiles. We would take the shapefiles provided to us from the research and geospatial teams and essentially build out the data that we needed for our website. ADUSearch 1.0 was a completely static website. So folks who are not familiar with web development lingo, A static website is one in which there is no interaction with the server once a page is loaded on your device. So the server will send you page content, and then everything else that happens on that page is between you and your web browser, and there is no two-way communication. There's no return trips back to the web server. That limits what we can do in some cases. And it definitely imposes some challenges on us, but it has a lot of advantages, and some of those we'll get to when we talk about scaling this project. But I did want to call out that it was a static website. We visualized the data with the Mapbox API. That was a choice that we made based on sort of our experience with Mapbox and their placement as the industry leader for web visualization of geospatial data. We started with Mapbox, and the capabilities that they offered us turned out to be sufficient not only for ADUSearch 1.0, but also completely within the scope of what we needed for ADUSearch 2.0. So a really good product, really solved a lot of problems for us, and I highly recommend Mapbox. So the goals of this project were to prove the concept, not only to prove the research concept, but to prove that we could present an attractive and useful visualization. We really wanted to nail the visualization and build our internal capacity to support this type of application, because of course we knew that there was a possibility that a larger project would be approved, and that going forward to ADUSearch 2.0 might be a thing that happened. We learned some things in this process that I think really helped us prepare for the second phase. Manual processing of spatial data is extremely labor intensive. And we knew going into ADUSearch 2.0 that the things that worked for us in ADUSearch 1 were probably not going to be sufficient. Just based on our experience of working with that data for one single municipality, we knew that when we turned to dozens, it was potentially going to be a problem to try to do things the same way. We proved that Mapbox was capable and suitable for the work that we needed it to do. And we identified that source data is challenging. Even working with only one municipality, and the City of Windsor actually is a leader in open data, has an excellent open data portal, and provides lots of usable data in pretty good formats. And even with those advantages, it still was a challenge and required a lot of iterative work, a lot of downloading of a candidate file, processing it, visualizing it on the web, and then discovering problems. So we knew we were going to need, well, essentially what the last bullet point identifies. We knew that if we were going to do this on a national scale, we would need to have a data transformation pipeline that automated as much of the work of dealing with those shape files, or in the case of 2.0 GDB files, that we would need to automate as much of that as possible in order to have a shot at succeeding. So those were the lessons that we learned. And fortunately enough, ADUSearch 2.0 is something that was supported by the funders, so we were able to embark on this project. And ADUSearch 2.0 is more of everything than ADUSearch 1. Dozens of municipalities in the end will probably end up in the triple digits. The data is more complex. There is a lot more information that we want to communicate to users of this platform, not only within the detailed sidebar on the specific visualizations we supported in 1.0, but also whole new visualizations and whole new visualizations for every municipality, and a whole new model for visualizing some municipalities, because when we do get to Quebec, we haven't quite gotten there yet, but when we do get to Quebec, they have a unique regulatory environment in that province, and it required a whole lot of additional work. So a lot of complexity there. And finally, we had to support more languages, twice as many languages, as a matter of fact. ADUSearch 1.0 was a monolingual English-only website. We were not going to be able to do that for a Canada-wide project because we do have 2 official languages. So we knew we were going to have to support both English and French in this application as well. Our goals in ADU 2.0 were to produce an architecture that would scale, not only scale in terms of supporting a larger number of municipalities and all of that processing, but also support a web application that is now national in scale. Rather than an application that we knew had a potential audience of the population of the city of Windsor, we now have a web application that has a potential audience of the entire population of Canada. So we had to be ready for that. We also knew that we were going to be storing data for the long term in ADUSearch 2.0, more on that a little later, and we needed to invest in security, and we did quite a bit of work to ensure that our data pipeline and application backend are as secure as possible. And finally, and I think the most important goal was to produce a self-service data pipeline. In ADU 1.0, there was an awful lot of close communication between the teams as we moved data through the process to visualization. We knew that that level of back and forth was not going to be possible with so many municipalities that we had to support in ADU 2.0, and at some points the pace of delivery of municipalities can be quite high because there are a lot of people working on the GIS side on this project. So a data pipeline that end users in this case being the GIS team, would be able to upload data themselves, get the feedback on the processing of that data themselves, and hand it off in a clean and automated way. So the architecture that we landed on, this is an extremely zoomed out view of our architecture. And essentially what I wanted to do on this slide is give you a sense of all of the pieces of this application and how they relate to each other. And we'll get into detail on each one in subsequent slides. So the administrative backend, just to start at the upper left, is the part of the website that only the ADUSearch team ever sees. This is the piece of the web application that is concerned with uploading of new data, checking the status of data that has been uploaded, downloading required files for the web application and so forth. That's what lives in the administrative backend. The administrative backend allows users to upload data, which of course we then have to store. And that means that we throw that data into our raw data store where it is accessed by our data pipeline, which is the process that takes that source data, those GDB files, and turns them into all of the different data artifacts we need to support the website. And the data pipeline communicates with our production data store, which is our database that stores completed municipal data for all municipalities, okay? That is the data store that is not structured in any way related to the source GDB data. It is a structure that is convenient for us and for our development process. The production data store, data from that data store is used in our communication with Mapbox. We'll get into the details of exactly how we leverage Mapbox a little bit later, but essentially we have to create map tiles. If you've ever worked with Google Maps or any of the other major web map providers, you may have noticed that when you use your scroll wheel to zoom in and out, that the map is actually rendered on your screen in squares. And those squares are called tiles. And each different zoom level, each different tick of your mouse wheel to zoom in or out on the map is a different zoom level and requires a completely different set of tiles. Those are the things that we are generating using Mapbox. And the static site generator also requires data from our production data store. And the static site generator is our tool that takes the processed geodata from our production data store, along with a bunch of artifacts that are downloaded from our administrative backend, and processes them to generate all of the static web pages that are required to serve the application, okay? And all of that, once all of that is done, we populate those static pages onto ADUSearch.ca, and you can see that there is also a blog component there. There is a non-static piece of ADUSearch.ca that runs WordPress, and I'll get into some detail about that and why we made that choice to split the responsibility for the public-facing website essentially into two different applications. So that is the high-level architecture of ADUSearch.ca. There's a screenshot of our admin backend. As you can see, we did not apply the same loving touch to designing a wonderful and beautiful user interface. This is an application that a handful of people will ever interact with, so we figured that that was what we needed. So this application is written in Ruby on Rails. The reason that we use Ruby on Rails is that it is an excellent tool for rapid application development. And the administrative backend, we needed a website for it. We needed a tool that would be robust and work for our users, but we did not want to spend a lot of time painstakingly building an application that was going to serve a small number of users when there are options available like Ruby on Rails, which give you a lot of free lunch as long as you're not too fussy about what's on the plate. And that was perfect for us. This tool is used for end user file upload, but it also handles job dispatch and reporting. So we break the processing of a geodatabase file down into a number of tasks, and each of those tasks is defined as a job. And we use Sidekick, which is a module, a Ruby on Rails module and product. We use Sidekick for job management. And what Sidekick does for us is handle all that complexity of managing the infrastructure of running jobs and determining their status, whether they succeeded or failed, and what that means and who should be communicated with. All of that we got from Sidekick, mostly for free. So the administrative backend component was something that we knew had to be good and useful and do its job, but we wanted to develop it as quickly as we possibly could so that we could focus as much attention as possible on the public-facing pieces of this web application. So you ended up with a Ruby on Rails app that is nothing to write home about in terms of looks, but does the job. We have two data stores in ADU Search 2.0, a raw data store and production. The raw data store uses Amazon S3, which is a very reasonably priced way to store data for the long haul. If you think of it as similar to the kind of file sharing tools that you may use in your everyday life, you're on the right track. It's if you can imagine a Google Drive or a Dropbox that you primarily interact with through the software that you write to deal with it, you're pretty close to what we're dealing with S3. We use it to store raw GDB data, the processed JSON files, so the files that our administrative backend tells our job engine to produce, so that we can provide all of those JSON files that the web application needs. Those are stored in S3. And finally, the tile data, prior to upload to Mapbox, the tile data is also stored in S3. The production data store uses Amazon RDS, which is a way to get a relational database server without having to maintain the relational database server. It's an excellent tool. For our database engine, we chose PostgreSQL with GIS extensions to support the geodata that we knew we were going to get, and it is the tool that stores our processed geodata. So that you may, if you're a software person, you may be thinking about our application architecture and our process and what we were working with, and asking yourself why we needed a relational database. And this was something that we actually debated quite a bit as well. The relational database is not strictly necessary. Everything that we need to produce those processed JSON files and tile data exists for us at the end of our processing pipeline. So we theoretically could have generated the data that we needed, generated those JSON files then and there, and bypass the need for a database. In practice, what we found is that having a database that mirrors the GIS data that is in our production web environment gives us a whole layer of visibility into that data that has been invaluable in troubleshooting. And the other thing that it gives us that is a nice to have, but certainly has been nice for us, is it gives us the ability to maintain the version history of that geodata all the way back to the first time that a particular municipality's data was uploaded to the database. So if we ever have a problem with a municipality that we don't catch, for example, in our validation, our automated validation process, and it actually landed on the website, well, we have the ability, without getting a new GDB from the client, we have the ability to revert back to an older instance of our data in our production data store. Now that's theoretical. It's not something that we've had to try yet, but I wanted to just kind of paint the picture for you of the additional capabilities it gives us to maintain that RDS store. And the heart of our application, and one of the biggest pieces of work that we did, was build out the data pipeline. So all of those jobs that get thrown out by Sidekick as part of the Ruby on Rails application have to land somewhere, and where they land is with our Python command line interface. So we built a Python application that handles all of the tasks that are required to process this data, as well as generate the map tiles and essentially everything that needs to be done to take this data from the raw GDB that we get from the GIS team to all of the files and so forth that we need for the web application. And we built it as a command line interface so that we could interactively execute tasks as well. And that's another way that we as a technical team can support the web application and support the ADU team, is we have the ability to jump in and manually run steps as needed. It has been really helpful for us in troubleshooting when you can, from the command line, execute a command and know that it's running the exact same code that is running on the administrative backend. Really been helpful for us. I mentioned that our task runner is Sidekick on a previous slide. One of the most important things that we do is validate incoming data against a known schema. I think that one of the things that you should be, the impression that you should have from Chris's talk is that there is a ton of very detailed work that needs to be done in order to produce a GDB file that is usable. And inevitably, there are going to be challenges. There are going to be times when the tooling that is used to produce that GDB zigs when it should have zags, or someone makes a typo, or some of those type of things. Very small things that could result in a bad visualization or inaccurate data showing up on the website. So we wanted to avoid all that, and we validate every GDB coming in against a sort of a set of known parameters and requirements, and anything that doesn't pass gets rejected. That upload is rejected, processing stops, an alert and an error message is sent back to the user so that they can understand what they need to do to remediate that. And then they have to sort of start that process again with a fresh upload. The pipeline blesses good data and marks the most recent version safe to use in the database. That safe to use marker is really important, and that is the way that we could manipulate the version of data that we are dealing with. If we ever had to, we could manually kind of manipulate which version of the data is safe to use and which isn't in order to get the output that we want. The last thing I wanted to mention is Tippecanoe. And this is a little bit technical, but if you're thinking about using any of these tools, it may be valuable to you. Tippecanoe is the command line tool that Mapbox provides for processing geospatial data and turning it into the tiles that they expect on their tile server. Mapbox will generate tiles for you. It costs money, or you can use a tool like Tippecanoe. We ran into a problem. We ran into a problem with 3 map tiles in Toronto. At the most zoomed out level, there were 3 tiles in Toronto that were too dense to visualize. There were too many kilobytes of data in the given tiles, and Mapbox wouldn't render it. We made some compromises, did some things, and got Toronto working. But in the process of researching it, we are aware of a product from Mapbox, which the name escapes me right now. Unfortunately, I didn't put it in my notes, but there is a new product from Mapbox that Mapbox Tile Services, MTS, that allows for much larger, much heavier tile data, 2.5 times the data inside a tile, which would certainly have solved our problem. But unfortunately, that project is still in beta. So at this time, you have a 500K limit. 500K of data is what you are allowed in one given tile. That jumps up to over 1 megabyte when the Mapbox tile service is released. The static site generator that I mentioned, written in PHP. So one theme that you may be noticing from my presentation so far is that Parallel 42 is pretty comfortable working with different tools and in different programming languages. We're very comfortable using whatever tool makes the most sense for a given piece of a project. And in this case, it made a lot of sense to build the static site generator in PHP. And based on the JSON data that is generated by the data pipeline and presented in the administrative backend, the static site generator uses those JSON files to build out the municipality landing pages and map pages. So once we've got that static site, then we're off to the races, and that's what you'll see in your browser. Mapbox, I mentioned them before. They're a great partner. They have an excellent product, and you've got a little screenshot there relating to some of the tiles, what the tiles look like on the back end for different Canadian municipalities, and you can see the size of those municipalities in square kilometers, which is kind of interesting. One of the things that was kind of nifty to discover is the way that Mapbox calculates the sort of the area of a municipality is based on the area of the tiles, not the area of the municipal boundary. So we had some interesting surprises there when we were estimating what it was going to cost, for example, to do certain operations, and finding out what a square kilometer means to Mapbox. So that may be something that is valuable to you in the future if you ever work with Mapbox when you're estimating those costs. And finally, the web front end is the visualization tool, and we split that into 2 subcomponents as well. We have a static site, which is the landing page, all municipal home pages, and all map pages. And the WordPress site is basically for everyone else. And the advantage that we have here is that we get the best performance possible for the most visited pages, which is the landing page and those map pages. And we also, from WordPress, we get the ability to allow end users to log in and make changes to the content themselves. And that makes life a lot easier for the ADUSearch team. We don't have to go through any kind of process back and forth between the organizations in order to, underline something on a blog page or on the contact page or update something. That's all stuff that can be done by self-service, and that's the reason why we use WordPress for that piece of the website. So that is essentially the high level view of this application and the back end and how it all works together. Just a couple of words about scaling the application. I'm just going to zip back here. So there were a few things that we were concerned about in terms of scaling. One was our ability to process data in a timely manner. When we worked on ADU 1.0, it would sometimes take an extended amount of time for us to take shapefile data and turn it into what was needed on the web page. And we were concerned about performance. We ended up with a pretty modest infrastructure in terms of the actual VMs that we have to host, the virtual machines on Amazon services that we have to host. So from a backend perspective, all of this stuff is pretty well within parameters for the type of thing that Amazon does really well, and really there were no real hiccups whatsoever. On the website, of course, scaling is related to the number of visitors you have. The number of people in a given period of time that visit your website is going to determine how many resources that you need. When we built this site, we knew that we were concerned about scalability. We had built a local web application before. We weren't exactly sure how much traffic we were going to see. So we also felt that having a static site was going to allow us to feel a lot more confident, because most of the work is actually done by the end user's web browser. We upload those tiles to Mapbox, and our web server never sees them. The tiles themselves come directly to the browser from Mapbox. So all of that performance is managed by between the local client web browser and Mapbox. So at the end of the day, the only thing we had to worry about was the static or the website itself not tipping over under high traffic. For that reason, we built a static website. What we found is that with one single web server, given the size of hardware options that we have on Amazon Web Services, that we can likely, with one single web server, manage all of the traffic that ADUSearch could possibly have to see. We did some testing, and we found that our web application was able to handle more simultaneous users than OpenStreetMap, which has billions of users worldwide, than OpenStreetMap sees on a sustained basis. So we're pretty confident that that single web server is going to be able to handle whatever gets thrown at it. And in the case that there is a challenge with that level of performance, we would be able to bring in a load balancer and add multiple servers, multiple web servers, in order to serve those static pages up to more people. But that's just not an eventuality that's happened. So that is the the alpha and the omega of the web and data pipeline piece of ADUSearch. So with that, I am going to stop sharing my screen. Thank you so much, everyone, for joining us. Thank you very much to Fraser and Chris for joining me and presenting tonight. We're all really excited and proud of the work that we've done together on this project. And again, thank you all for being a part of it and joining us to celebrate it tonight. Thanks again.